Hey everyone, welcome back. This is part 2 of the bonus lecture on tricuspid atresia and calculating the QP to QS. In this video, we'll go over the QP to QS equation, and then we'll look at a couple of examples on how to calculate that and the scenario of the tricuspid atresia patient with pulmonary overcirculation versus the TA patient with pulmonary insufficiency. Enjoy. So the QP to QS equation will give us a ratio of blood flow going to the pulmonary circuit versus the systemic circuit. Q meaning quotient, so quotient of pulmonary blood flow to quotient of systemic blood flow. You can imagine that in an ideal scenario, this is 1-to-1, so equal amounts of blood flow going to the lungs compared to the systemic circulation or vital organs. This is an equation derived using the Fick equation. I won't get into that here, but there's a YouTube video that I can give you if you're interested. I'll send you that link where it shows you how this equation is derived using the Fick equation. But for the purposes of this, a little bit higher level than we need to dig into. There are a number of ways to calculate the QP to QS. Most commonly, you'll see us do this at the bedside using arterial and venous blood gas samples. That's the least accurate way, and we'll talk about the assumptions that you have to make when using that method, and those assumptions mean that this ends up being the least accurate way to calculate this. It gives you an overall big picture idea of what the ratio of blood flow is, but it's not the most precise measure. More precise would be by echocardiography at the discretion of your cardiologist, and then most accurate would be in the cardiac cath lab, where each of these components, blood can actually be sampled in order to obtain precise values for each of these components. So what are these components? Let's talk about those for a moment. The SaO2 is the oxygen saturation of arterial blood at the level of the aorta. For us, we use, when we're calculating this at the bedside, we use the surrogate of a blood sample either from a UAC, an umbilical artery catheter, or a radial arterial line. And that is a pretty accurate surrogate for us to use. The mixed venous oxygen saturation, or SMVO2, is that oxygen saturation of blood flow typically at the level of the SVC to RA junction, or IVC to RA junction. In a patient with no mixing lesions, you can obtain this from the right atrium, and that's a pretty accurate mixed venous O2 sat. You can imagine that someone with an ASD who has mixing, mostly, even if it's mostly right to left, they will have some left to right shunting, and that actually throws off your mixed venous O2 sat. And so for our patient, the tricuspid atresia patient with an ASD, you would actually want this. If you have a UVC, you would want the line to be sitting in your IVC, not at your IVC to RA junction, and certainly not in your RA. Or if they were to have an IJ, you would want this sitting in the SVC rather than the SVC to RA junction or the RA. The SpO2 is the pulmonary venous oxygen saturation, so that blood in the pulmonary veins coming immediately from the lungs and towards the left side of the heart. And finally, the SpA02 is the oxygen saturation of the blood in the pulmonary artery. We'll talk about assumptions that you have to make in order to obtain the SpO2 and the SpA02 if you're doing this at bedside using your venous and arterial blood gas samples. So we've gone over the components of the QP to QS equation. Now let's look at an example of a 24-hour-old tricuspid atresia baby who has an umbilical artery catheter, UAC, as well as an umbilical venous catheter, UVC. This would also work, of course, if you had an IJ for your source of venous access, or if you had a radial arterial line for your source of arterial access. But we'll assume that our 24-hour-old baby in the NICU has umbilical catheters for us to use. Before we jump into the actual numbers, let's talk about a couple of assumptions we have to make in this scenario. This baby has essentially a single ventricle, right? We've talked about the RV hypoplasia and a tricuspid atresia child, essentially making this child single ventricle. The LV will be the source of blood flow to both the pulmonary and systemic circulations. And so knowing that, you can buy that the SaO2 will be equal to the SpaO2, right, as blood, it mixes, and that the LV ejects, and then blood will go one of two paths, either the pulmonary artery or the aorta. So those numbers are equal for the single ventricle patient. Another assumption that we're going to need to make just using our blood gases would be that the SpO2 in an otherwise healthy set of lungs should be between 98 and 100%. This is a rather big assumption to make, but I think a safe one to do in the 24-hour-old tricuspid atresia baby who has no other comorbid conditions and certainly no lung disease. As a patient with this condition developed perhaps ventilator-associated lung injury or pulmonary edema related to pulmonary overcirculation or things like that that will cause direct lung injury, this assumption may not be accurate, and so you just have to be cognizant of that. But our 24-hour-old baby, who we'll assume is not being mechanically ventilated, not on supplemental oxygen, this is a safe assumption to make. So we've drawn a blood gas from our UAC. You see our pH, our PCO2, our PaO2 here, and then the oxygen saturation of the arterial blood in this situation we'll say is 90%. Then we've also drawn a venous blood gas. It's ideal to draw these at the same time, mind you. So we've drawn a venous blood gas from a UVC that terminates in the IVC. You see our pH, our PCO2, our PO2, and our mixed venous oxygen saturation, which is equal to 60%. And so let's plug these numbers into the equation. The SaO2 of 90% minus the SmVO2 of 60% over the SpO2 of 100% minus the SpaO2 of 90%. So that gives you 30 over 10, which equals 3 to 1. So what this tells us is the quotient of pulmonary blood flow compared to the quotient of systemic blood flow is 3 to 1. So this is a scenario where we're seeing pulmonary overcirculation in the tricuspid atresia patient, likely one with a very large unrestricted VSD. So let's look at an example of a patient with pulmonary blood flow insufficiency related to their tricuspid atresia. So let's use the same example, the 24-hour-old baby in the NICU with tricuspid atresia. We have gotten our day of life 0 echocardiogram, and we see that they have a very small restricted VSD. We have gotten UAC and UVC access for us to draw blood gases and compare QP to QS once again. And so let's look at our numbers here. From our UAC, we can see an SaO2 of 70%. From our UVC, which is terminating in the IVC, we see an SmVO2 of 50%. Again, we make the same assumptions that we did in the previous slide, right, where our SaO2 is equal to our SpaO2, since this is a single ventricle baby. And we're also assuming healthy lungs that haven't been injured perhaps by mechanical ventilator trauma or pulmonary edema related to pulmonary overcirculation, all of those types of things that may make your SpO2 lower. Here we're assuming a healthy set of lungs, and so we'll treat our SpO2 as 100% for this example. So let's plug all of those numbers into our equation. Our SaO2 minus our SmVO2 will be 70 minus 50%, and then our SpO2 minus our SpAO2 will be 100 minus 70%. That gives us 20 over 30, or a QP to QS of 0.67 to 1, or 2/3 pulmonary blood flow compared to systemic blood flow. And so you see this is a good example of pulmonary blood flow insufficiency. This would be an example of a baby where you would definitely need to start Prostin, and if this baby is already on Prostin, you need to be getting an echo to look at the patency of your PDA. You will need to be considering things that can lower your pulmonary vascular resistance as well. So perhaps providing supplemental oxygen, correcting an acidosis, considering agents such as milrinone or INO, they're pulmonary vasodilators that might help you have more balanced circulation as well. All right, everyone, that concludes the second of this bonus lecture series talking about QP to QS. We've considered the baby with tricuspid atresia, both in the scenario of a large unrestricted VSD and pulmonary overcirculation, and what that QP to QS equation might look like, as well as the baby with a very small restricted VSD and pulmonary insufficient blood flow, or what that QP to QS might look like. I hope this was helpful. Please reach out with any questions, clarifications that you might have. Next lecture will be week 3 of the congenital heart disease series. Thanks for tuning in.